maybe part of this is very simple for you guys, so I will try to do the balance the best way I can. Okay, so as you all know, 4th of July 2012, we have great fireworks, and the previous was an event from CMS, but this is an event from Atlas, 2 electrons, 2 muons. Was the discovery of a new type of particle that we have never seen before, and was a discovery of a new type of force that basically is proportional to mass. And so this was the start of a new era for particle physics and cosmology. So as you know, this discovery was possible at the Large Hadron Collider, LHC at CERN, which ran for 2 years as a proton-proton machine. This is beautiful Geneva and France. And this is Mont Blanc there in the back. And whenever I look at this build, the thing I think about is that I broke my knee there skiing, but okay, besides that, everything is great. And so this is a 17-mile long pipe, 300 feet underground, where you collide protons against protons at the center of mass energy of 8 tera-electron volts. And so this machine is the most expensive and most complicated and most ambitious machine ever built by mankind. And so we have here something like in 2011, 2012, about 400 million collisions per second. And in all these, we only produce about 600,000 Higgs. So the Higgs are very rare. So how do we look at this? Well, we look at these collisions that are, this amount of collisions per second with very powerful detectors. Detectors really are just are like cameras taking pictures, but they are very special cameras. They take 20 million pictures per second, and they're 3-dimensional pictures. So they are really huge, complex objects with cutting-edge technology. And as a theorist, I'm always amazed that these things work. But they do. So this is the Atlas detector. This is here you see that is actually about 6-story high. So this is a gentleman there. And is as heavy as the Eiffel Tower. The other detector, that is CMS, is twice as heavy as the Eiffel Tower. And so this is a collaboration. The Atlas experiment is a collaboration with about 3,000 physicists and 174 institutions and about 40 countries around the world. So it's a truly international endeavor. And of course, the NYU group has done a lot of important contributions to what came as outcome from the Higgs discovery in the Atlas detector. So this is the CMS detector, the little one. So it's compact, which means it's half the size of Atlas and twice the weight. And again, about the same amount of people involved. So altogether, there are about 6,000 physicists involved in this. So this is just to show that US plays a leading role in LHC discovery. CMS is 1/3 of US contributions, so it's the largest contingent. So there are 40 countries, but US plays a really, really leading role. And in Atlas is 1/5, and they play leadership roles. In particular, Kyle here is actually playing a leading role in as convener of the US side of the Higgs group, correct? Well, here I think he was, this is deGrasse Tyson, no? So I don't know what you were doing there, but probably were not searching for the Higgs, or yes. Celebrating, yeah, celebrating the discovery. I thought it was a cute picture of you. Anyway, so now getting more serious. As you know, as I said, the 4th of July, the Higgs really made the front page of all the newspapers, and even here in your local newspaper, you had some news about the discovery of the Higgs and what happened at CERN. And indeed, the 2012-2013 has been a revolutionary year for physics. And just 10 days ago, the Nobel Prize for Physics 2013 went to Mr. Higgs and Mr. Englert. And so I like these pictures because I think it has to do with the personality of the two people, Belgium and British. As much as I know them, that I don't know them so much personally, but okay. So what is important for us is that how we test which of these theories is right. Well, both options will change the way the Higgs behaves. Okay? We have discovered the Higgs. Now we need to understand very well the properties of the Higgs to know which of these two options could be the solution of the problem. And of course, these two options will come with different type of particles that we can look for at LHC. And this is really the next step for LHC. So in supersymmetry, I will go not very, the issue is that now I have all the standard model particles, and I have all the supersymmetric particles. As I said, for every fermion of the standard model, there is a boson, and we call it very elegantly super up quark, or SUP, or super top, or STOP. Okay, STOP is a nice name. For the gauge bosons, they are going to be what we call gauginos, that are fermions. And for the Higgs, in fact, there are going to be more than one Higgs. For the Higgs, they are going to be a fermion that is a Higgsino. So for every fermion, there is a boson. And the important part is that if supersymmetry is exact, they have equal mass and couplings. Well, if they have equal mass and couplings, I show you this formula, okay? And if I put any number of other theories, particles, but for every fermion, I put a boson with, actually this is the coupling of this fermion to the Higgs, and this is the coupling of this boson to the Higgs, with the same coupling to the Higgs, then you see right away that this goes to 0, correct? So this is really what happens in supersymmetry. In supersymmetry, this goes to 0. However, unfortunately, LHC, as my husband looks to make a joke about, Kyle has not worked hard enough and has not discovered supersymmetry yet. Is that true? So my husband says experimentalists are being totally incompetent. I have not discovered supersymmetry when we know perfectly well that it's there.
MD is working on it, right?
He's working on. I don't know. He was dancing, so I don't know. Anyway, the point is, okay, that in supersymmetry this cancellation is automatic, but we know that supersymmetry has not been discovered yet at LHC. Okay, and what this means is that there is some difference between the super partner, let's say the top, and the stop, because if they would have equal mass, I would have seen it. Okay. In particular, there are other, like selectrons and other of the quarks, okay? So this difference is between, let's say, the top and the stop, okay? And this difference is what we call of the order of the supersymmetry breaking parameter. So we need to break supersymmetry. We call it softly, but that means that we are going to change to give a mass, different mass, to the standard model fermion than to the bosonic supersymmetric partner, but we are going to keep the same relation between the couplings. Okay, and this is what we call soft supersymmetry breaking. So, why I'm talking about the top so much? Well, because of the Yukawa, correct? The top is the one that couples more strongly to the Higgs, and therefore the top is the one that is most relevant in this game. So we are looking very much for the stop. Because if we want to solve this problem of naturalness, we need to have a stop that is not much above maybe a few or 10 TeV. And that how much fine-tuning is a question of taste. So this is the idea why we thought about supersymmetry, and most important, why we think that supersymmetry should be at LHC reach. Okay? But there are other reasons why, besides this, why we think that new physics could be good, and it's because the standard model has problems explaining all these issues, explaining dark matter, the matter-antimatter asymmetry, the origin of the neutrino masses, the origin of the actual process of a spontaneous symmetry breaking, because I didn't tell you, but in reality, in order to have a spontaneous symmetry breaking, in the standard model, by hand, I have to put a negative square mass parameter in the potential. Okay? And the idea is that in supersymmetry, you could make that happen dynamically through quantum corrections. Okay? The issue of unification of forces is also something. So supersymmetry can address some of these questions, can give a nice dark matter candidate, can have a solution for the matter-antimatter asymmetry, can have a good solution for dynamical electroweak symmetry breaking. So back to the Higgs, the basics that we want to understand is, are the Higgs couplings to matter particles proportional to their masses? Does the Higgs talk to particles that we have not seen? Okay? Does it decay to dark matter? Does it decay to other particles? Or does it interact with other particles? This is, we have discovered the Higgs. Now we want to get the most out of it to understand what is the theory that is solving all these puzzles, all these mysteries of matter that we have. And of course, as I said, very important, are there other Higgs bosons? How many Higgs bosons are there? We just found one. Okay? Could be that there are more, and that they share their job, okay, in giving mass to the particles. And then there are the big questions that the point is, now we have found the Higgs. Are these big questions of particle physics related in some ways to the Higgs? And in that way, is there a Higgs portal to dark matter? Does the Higgs talk to dark matter? Okay. Does the Higgs trigger this genesis of matter? So it's related to matter, and I will go to that in what? Okay. 5 minutes? Oh God, I won't go. Okay. And does the Higgs make the universe unstable? And I underestimate my time badly. Or I'm too relaxed, I don't know. Okay, so what we have measured the Higgs. We know that the mass is 125 GeV with some error, plus minus 1 or so. We have 3 options that I showed you about before. This is the mass of the Higgs. This is a 125 GeV. So if the standard model is valid to the Planck scale, the mass of the Higgs could be in principle in all this range, but it happens to be where the red line is. And interesting here is that what it is on this blue area here is, and in fact that is over the red line, implies that we are living in a unstable universe. So the vacuum where we are is not stable. Okay? In fact, it's metastable. So if there's nothing else besides what we call the standard model, then we do live in a metastable vacuum. I have good news for you, because I don't have the time to tell you all about it. This metastable vacuum is very long-lived, about 10 to the 100 years, so we don't have to worry about our kids or great-great-great-great-great-grandchildren. But it's an interesting point, okay, that we want to understand. Is this metastability of our vacuum telling us something else or not? Okay? And this is what I try to see here. So we are here, and by analyzing the Higgs potential, we understand how this quartic coupling, the self-interacting coupling, works, and it happens that it has a 0, and this is related to being like here, at some energy, 10 to the 10 GeV or so, at some field value. And so there is another vacuum, deeper than our vacuum, and the question is, are we tunneling? What is the time that will take us to tunnel to the other vacuum that will destroy our universe, of course? And as I said, the good news is, because this evolves so slow, is that the electroweak vacuum is safe from early collapse. So you don't have to panic. In supersymmetry, we have different options. This is like what we call the minimal extension, which means that we only add the minimal amount of particles to the standard model. Of course, you say, well, this is a disaster. For every fermion you put a boson, you are doubling the number of particles in the standard model. But we already went through this disaster once, when we realized that every particle has an antiparticle. Okay? So the only problem here is we have only found half of the particles of the supersymmetric standard model. But anyway, the Higgs mass in this minimal supersymmetric standard model can be 125, but of course, what this tells us, okay, is that you are going to be in a very specific region of parameter space. So we want to learn what this 125 GeV mass tells us about supersymmetry.